Trends of Advanced Water Supply System Technology. This lecture will allow you to understand and apply technological trends in the operation of advanced water treatment facilities and water supply pipe networks. I will talk about the trends in water treatment facility technology, trends of water pipe network management technology, and future technology development and policy recommendations in order. Trends of water treatment facilities technology. In Korea, water supply systems are largely classified into general water supply, wide area water supply, local water supply, and village water supply. There are 504 intake facilities and 490 purification facilities, and they produce a grand total of 27.2 million tons of water per day. Our current issue is aging facilities, especially those that have more than 30 years of operation history. There are 210 of them, and 17 of them are mass-producing facilities for wide area water supply. We must secure water quality for those mass-producing systems. We've serviced water supply since 1907, so there have been many changes and technological developments in the Korean water supply system. We have more than 540 regulatory standards for safe drinking water quality, which include standards for potability, 1,4-dioxin, phenol, and microorganic substances. Our engineering focus is on restructuring and rebuilding water supply into a distributed and smart system to satisfy those standards. To quote the 2020 Water Supply Report from the Ministry of Environment, there is 200,000 kilometers of existing water supply pipeline. At the end of 2017, total length of water pipeline was 209,000 kilometers, and 97% of existing pipeline was for general water supply. All the wide area systems for developed cities accounted 2.6% of it. This number is increasing every year. By age, 32.4% of existing pipeline has passed the 21-year criteria for age pipeline. 12.9% of total existing pipeline is just below that, aged 16 to 20 years old. Pipelines that are aged 11 to 15 years make up 16% of the total system. 21.6% of pipeline has under 10 years of usage, and 17.2% of total pipeline falls under the 5-year criteria for newly established pipelines. If proper investment in water pipe network is not made, aging is expected to accelerate in the future. Since 2000, maintenance and repair expenses have surpassed expenses for newly installing water supply. Those advanced systems were applied to the Daegu and Busan wide area water supply as a national priority. The water supply systems there had been affected by worsened intake water quality, which was caused by rapid industrialization. Nowadays, all water supply systems with 3rd or lower rated intake water quality levels utilize advanced filtration systems. In particular, if phosphorus, 1,4-dioxane, or perchlorate traces are found in intake water, those systems are prioritized for advanced filtration systems. Those pathogens are high risk factors for water quality failure, and they require highly customized treatment. We provide a mix of AOP, ozone, activated carbon, and NF/UF, RO membrane filtration customization for such water systems. As advanced filtration targets clean water for industrial and domestic usage, the most important factor is control systems for colloidal particles and soluble microorganic matter. This is done with physical filters called a membrane process. Membranes for this process are expirable, so engineers must monitor and control membrane failure at the end of system. To secure safety factors for chlorine-resistant pathogens, ozone and activated carbon filter treatment and ionization are our favored tools. All these processes are measured at the micro level, so complete assessment of water quality for the intake. Legacy general water filtration systems and advanced filtration systems without customization are not suitable for water quality maintenance for advanced industrialized areas. Recent water quality failures have come from industrialized areas and substances like 1,4-dioxin. Percolate and phenol can only be dealt with by using customized advanced filtration. This happens with aging pipeline networks, and the most recent case of a red water incident was the opening act of this work. Let me show a video report on such water supply failure cases.
인천 지역 수돗물 문제는 갈수록 태산입니다. 붉은 수돗물 사태에 이어 이번엔 비린내가 난다는 주민 신고가 이어지고 있습니다. 취수장 인근에서 발생한 녹조 때문으로 추정된다. 인체에는 해롭지 않다라는 게 인천시의 설명인데 주민들은 불안감을 털어내지 못하고 있습니다. 전현우 기자가 취재했습니다.
붉은 수돗물을 거르기 위해 필터를 여러 개 설치한 한 아파트입니다. 수돗물 색깔만 이상한 게 아니라 이번에는 비린내 같은 역한 냄새까지 나기 시작했습니다.
역쪽 냄새, 비린내가 나거든요. 그런 냄새를 맡으면 이제 과연 이 물을 먹을 수가 있을까? 씻었을 때 건강에는 지장이 없을까?
또 다른 아파트의 이 가구는 빨래를 아예 포기했는데 냄새나는 수돗물로 목욕을 한 가족은 피부병까지 호소하고 있습니다.
수돗물을 직접적으로 닿으면서 겨드랑이 이쪽이랑 목 있는데 이렇게 접히는 부분 쪽으로 좀 다 트러블이 나서.
지난주부터 시작된 인천 지역 수돗물 냄새 민원은 수십 건에 이릅니다. 인천시 상수도 사업본부는 최근 마른 장마로 해당 지역에 물을 공급하는 서울 풍납 취수장의 녹조 현상이 수돗물 비린내의 원인으로 추정하고 있습니다. 녹조를 해결해야 하지만 물을 공급하는 공천 정수장에는 고도 정수 처리 시설이 갖춰져 있지 않아 녹조 성분을 완벽하게 제거하지 못하고 있다고 해명했습니다. 환경부와 인천시는 그러나 물 비린내가 인체에 해롭지는 않다고 밝혔습니다.
위해성은 없고요. 냄새가 조금 나는 거죠. 그러니까 독성은 없어요. 근데 심리적인 물질이야.
인천시는 냄새를 줄이기 위해 수질 분석을 강화하고 활선탄 등을 추가로 투입하겠다는 입장이지만 인천시에 대한 주민들의 불신은 더욱 깊어지고 있습니다. KBS 뉴스 전현우입니다.
Trends of water pipe network management technology. Water supply technology has been developing in 4 areas: pipe network systems, retrofitting and detection of aged water supply, leak detection, and computerized maintenance management systems. Retrofitting and detection of aged water supply targets legacy pipelines that have more than 30 years of operational history. Computerized maintenance management system is introduced as an additional layer for existing physical facilities as it provides a real-time alert system and sensor monitoring. This technological shift will provide data for incipient disaster response and prevention, especially for critical and erratic events like urban flooding. This is concept diagram of block system for water pipe network secure zero suspension water supply. Block system can be implemented in mesh or dendritic design, former for urban areas and latter for suburban and rural areas. Block systems for water supply are tiered in 4 levels: large, medium, small, and maintenance. Large blocks are based on conveyance facilities. They are then divided by water intake basin. Small blocks are classified by drainage and final stage usage. Maintenance blocks are the subdivisions of small blocks. They are based on the specified needs of certain areas that are sensitive to water supply, like hospitals or highly integrated industrial parks. The end goal of a block system is to satisfy both geological demands and demand patterns for water supply systems with optimized management of supply, intake, and filtration facilities. This is concept diagram for standard waterwork block system. It's centered on filtration, conveyance, and drainage. Smart block system is being deployed in Seoul as model case. Smart network monitoring of water flow, quality, and pressure is the next generation technology of water supply monitoring. One of most promising development in pipe network system technology is self-supporting molding compound. This new compound technology uses petrolatum mastic to prevent leakage and pipeline failure, notably for atypical or irregular pipe linkage. For retrofit and detection of aged water supply, sewage lining technology render legacy pipelines into smaller yet more efficient components via inner lining insertion. Ground burst sidesteps cost-incurring excavation process. Even iron and ceramic pipelines can be replaced with this. One technology for maintenance of the water supply network is the replacement of pipeline valves with non-interruption treated water valves in areas where supply interruptions lead to high damage compensation, and there is concern about water quality accidents. This is leak detection technology using topological information and satellite photography for managing leakage in the water supply piping network. Future technology development and policy recommendations. This is the level of water infrastructure construction by country, according to level of national income. Building advanced water infrastructure requires an appropriate balance between total national productivity and water infrastructure investment. Recently, Korea's water supply rate has approached 100%, and the water supply market is changing. It is shifting from being construction-centered to operation-centered, and consumers are demanding a high quality of water service. Retrofitting of aged facilities and the construction of future water treatment facilities through the introduction of smart technology are changing the marketplace. To respond proactively to the new market, it is necessary to foster expert star companies in the water supply area. To solve difficulties with carrying out work due to insufficient national funding, and to ensure the efficiency of projects utilizing the expertise of civilian companies, we need to increase the activity of future civilian investment projects. Considering that water supply is a public work, private and public partnerships are being actively pursued. Particularly in developing countries, water supply from developed treatment systems needs to be expanded through OECD nations, taking responsibility for technological leadership and civilian investment. For foreign civilian investment for water supply projects, PPP structures should be used to ensure work for the public good, efficient use of civilian capital, and safe project execution. We have to work toward the digitization of the water supply and the use of sensor technology, IoT, drone robots, CPS, big data, and artificial intelligence to operate a safe water supply system. The government needs to make a plan for systematic support and guaranteed funding for the active use of smart technology in the water supply. I propose digitizing the water supply system using smart technology to allow for a proactive response system for accidents. This would allow for an ICT technology-based system for preventing water supply accidents and improvements to service through retrofitting of aged facilities. Thank you.